My computer, oh yeah, okay, it's good. So, guys, the significance of the problem. What are we actually trying to, what is the open question we're trying to answer, guys? In the past, I would say 10 years ago, my lab was focusing on building new computing paradigms, new computing architectures, and so on. And we were lucky, by the way. We were quite lucky. Some of our technologies are commercialized. One of them is probably the most distinguished one, is so-called perpendicular magnetic recording. Until recently, it was used in every disk drive technology. Even today, in most disk drive technologies, they use this technology. We were the first, officially, we were the first people who actually made it happen, made it work. So that we contributed to the field of the information processing. And still, as scientists, as researchers, engineers particularly, we always were excited to tackle new challenges, to find new challenges, and to go for most exciting problems. And to us, it seems, especially because we come from the field where we build new computers, guys, new computing paradigms, to us, it seemed to be probably the most exciting platform is a so-called brain-like computing. I'll tell you what it is. Today, there are probably, if you ask experts in the field, there are most arguably, guys, it's a controversial issue. There are three. It's still debatable, guys, but I would say most people would say there are three contenders for next generation computing architecture paradigms. Quantum computing, I'm sure you all heard of it. It's a very powerful approach using quantum physics to create parallelism in data processing. Infinite parallelism. You can achieve anything. Ideally, it's beautiful, but never been done yet, by the way. It's a very promising approach. Lots of investment been made there by top companies like Google, Facebook, but IBM particularly, but it's not there yet. It's still a dream. That's a reality. The next one is, of course, much more viable alternative. It's in-memory processing. So memory and processing are combined, done in one little element. That's definitely, it's already happening. That's gonna happen. That probably will be a big thing in the very near future. And the third contestant is a so-called neuromorphic and/or brain-like computing. They're a little different. There is subtle difference there. Actually, to me, it's not such a subtle difference. It's quite a significant difference. I'm not going to get into this if you're not expert in this, but if somebody is interested, feel free to ask me in the future. So it's a brain-like computing. I'll tell you what it is. Definitely, guys, as I told you, quantum computing does not exist today. It's a big thing, very hot. There are demonstrations. People invest trillions of dollars in this, but it does not exist. Brain-like computing has barely been studied, but it exists. It's the human brain, guys. It's human brain. For you to get in the comparative number, actually, I have some numbers in the next on the next slide. It definitely exists, guys, but we have no idea how the brain works. And the biggest challenge, the most important open question, why we have no idea about this, guys. We cannot get inside the brain at the level, at that precision level we need to understand the computing architecture, which is single neuron or even better. So in the human brain, on average, there are 80 billion neurons, guys. You have to connect to each neuron. I actually do something comparable, guys. Okay, look. Impact of this will be crazy, of course. You all understand, guys, right? It's a brain-like computing, of course. Information processing will change the world, right? It will be totally different world. We will be able to connect. Reciprocally, brain-like computing will also help understand how the brain works, which is very important. It will lead to many disruptive medical applications, as I will discuss a little later, guys. So the main open question, how the brain works, why we don't know how it works. The reason is we don't know how the brain works the communication between neurons in the brain, and there are about 80 billion neurons, as I already mentioned. It's a lot, guys, you understand, right? So the communication between all these neurons is electric field driven. Electric currents flow between all these neurons. There is a major parallelism and so on. So there are actually many scientists who believe brain computing does use quantum computing. It's most likely it's there. You know, it would be preposterous, but crazy of us to believe we can be better than nature. Nature's been around for billions of years, right? We're very primitive. What we know today is obviously very primitive. You know, the evolution optimized the brain so well. We cannot beat the brain. When we say quantum computing, we're actually trying to beat the nature. It's hard to believe we can do that, but we definitely can learn from the nature, from the brain. And to do that, we have to get inside the brain. But the problem is, that's the most important open question. How are you going to get electric signals from the neurons? Even not from every neuron, from a lot of neurons to understand the computing architecture. I mean, what is the dimensionality of the computing, et cetera, et cetera. The problem is you cannot control electric fields wirelessly, guys. That's why I'm sure you all know Elon Musk, you know, Tesla, SpaceX, and many others. And he has a company. He has one of his exciting endeavors is called Neuralink, a company where he's trying to connect human brain to artificial intelligence. And you know, they made a major demonstration last year, I believe, or 2 years ago. No, last year, guys, where they, summer 2020, where they made a pig to controllably move something, to do something, smell, to test it, make it smell something or something very primitive, guys. The investment was about $150 million plus, several years of intensive research. Of course, you know, hundreds of engineers, guys, working on it. And still, you know, barely could do anything. And the reason is they try to establish physical contact. They put wires in the brain, like everybody else does. So they managed to increase the number of wires they connected to the brain a little bit. So it was something on the order of 1,000 or a couple of thousand maybe. Nothing. It's nothing. It's zero compared to the $80 billion neurons, guys. You understand? So definitely not even close. And of course, that's why progress like this, it's very incremental. It's not real basic revolutionary science. So to be really able to understand the brain, we have to get inside the brain at single neuron level without using wires, wirelessly. So that's the main open question we want to find through state-of-the-art, through futuristic engineering, if you can say that, you know. So some of the open questions, by the way, why, for example, this actually well-known open questions with the brain and puzzling the community, particularly to the engineering community. So thermal management, temperature variations in the brain is less than 2 degrees compared to CMOS chips is on the order of 50 degrees Celsius. Fan out means how many elements are connected to each element. It's 100,000 compared to 3 or 4 in CMOS. CMOS is a conventional computing technology, right? Power use, by the way, guys, power used by the brain is on the order of 20 watts compared to 7 megawatt used by the computer, supercomputer, which can achieve whatever the brain can achieve, guys, which does comparable computation. Imagine how much smarter our human brain is. And you know, the 7 megawatt, it's a little electro station pretty much. And let me tell you, China and United States always compete for the best supercomputer. To be honest, I don't even follow lately. You may know better. Last year, it was Chinese computer the best. This year, I think it's United States, ours. It's Oak Ridge National Lab supercomputer. And that computer, literally, it's huge. It's gigantic because it needs so much power, guys. You can imagine. It's not very clever, guys. The binary processing and so on. It's pretty much quantitative approach versus qualitative approach, because we do something not very intelligently compared to our human brain. So that's our goal, guys, to understand how the brain works. So, hypothesis come up with a brain-machine interface. Guys, now to tell you about the credibility of our hypothesis, guys, not hypothesis, of the open question. Recently, DARPA, this particular project, by the way, is heavily supported by DARPA. We're supported by DARPA. In the past, we've been supported by all the funding agencies there are, most important ones for sure. NSF, I want to acknowledge NSF, obviously, Naval Research, Air Force, DARPA also, by the way, in the past. But this particular one, mostly DARPA and a little bit NSF and Air Force, but mostly DARPA, guys. And why? DARPA is an interesting agency. DARPA always funds high-risk, high-reward projects. And DARPA, as you know, DARPA is the company, the organization, not the company, the government funding agency, which created the internet the way we know today, launched the Mars rover put on Mars, guys, and did many other incredible things. By the way, lots of them related to computing, and they claim one of the interesting things I recently learned, they're the ones who created computer mouse. I don't know how significant it is. They think it's a significant achievement. But interestingly, a few years ago, they created this program. It's called N3. Next, I always forget, 3 N's there are, guys. It's next generation, neurotechnology, and non-surgical neurotechnology. Non-surgical means hopefully wireless. That's what, not hopefully, it's wireless. That's what it means. And crazy competition. So we were very lucky. We were one of very few teams selected for this, and they give pretty decent amount of funding, and with the idea that you can get more, but it's extremely intense. So every month, we actually have to deliver. Whatever we promise, we have to deliver every month. Guys, you understand? It's a crazy work. That's why we realize we all in our team depend on each other a lot. So if one of us fails, we all fail. So it's a major teamwork. The reality, I'm very grateful to my students and my collaborators who work literally 24/7 with even this summer, even during pandemic, these guys work every day. I feel bad. I made them, but I didn't really force them. They had that enthusiasm and the dedication to it. I'm truly grateful to them. There's no words I can say to express my gratitude to them, guys. So, but anyways, so surprisingly, now we actually went pretty far. We're in the middle of phase 2. I'll be honest, we can cut any time. We're the weakest link probably among the 5 teams left right now. The other guys are MITs, Caltechs, Johns Hopkins. There's no name smaller than that, let me tell you guys. And these guys have a lot of resources. They have shared facilities. You can much better than ours. That's why we actually try. This talk is also partially aims at this, to create that shared effort, guys. We need shared facilities, to shared work, and so we do need to work together, guys, to be big in engineering. Engineering today, done at single units, single departments, is not going to go far. It's very hard to push it forward, guys. That's the thing. So you see, that's what we're trying to do, guys. And it was to, again, they gave credibility to our hypothesis. They actually established this program, and they did. At the inaugural meeting 2 years ago, they did say, listen, guys, we think it's the most significant effort they've ever done, most significant the internet. For them, it's their purpose, their immediate purpose is to create a super soldier. That's what they call it officially. It's actually written on the internet. Somebody who will respond to anything extremely fast. And our in about 10 months, we're supposed to start, we're right now at that stage, on humans, on Air Force pilots, and we have to teach them to fly a plane under most dangerous circumstances, particularly when they land. So we will give them ability to think very fast, so they can make decision within a fraction of a second. To be precise, 100 milliseconds. Apparently, they say scientific studies show that if an air pilot can make decisions within 100 milliseconds, most of the crashes would have been avoided, guys. So that's our first test. We're going to give them a helmet. Air Force pilot will be wearing that special helmet, which will make him turn him into Superman, pretty much, guys. You understand? It's a crazy stuff, you know. That's why the project is extremely exciting. And let me tell you, guys, it's purely about advanced materials, intelligent materials. This I'll tell you about our capabilities, and then I will tell you what those intelligent materials are, why they are so special. So our capabilities, you know, we've been doing this for many years, guys. I told you we did quite a few, at least 2 big major groundbreaking things in our field, information processing, which I used commercially implemented. They actually, on the internet, I was pleasantly read, it's not modest to say that cloud computing became possible only because of perpendicular recording, something we created, guys. So we're very proud to do this. We've done some pioneering stuff in the field, in the industry. But we hope this will be our most pioneering thing. So now, so we have all the expertise, but now being in Miami, we need more shared facilities again. That's hopefully this Frost thing will help us as well, you know, and others, you know. We have a new dean. Hopefully, he will support our effort, and he's been supporting so far. And we again hope we will grow in this field together, only together. By the way, remember. So, what advanced materials? What exactly intelligent materials? Our expertise. Intelligent materials, guys, or sometimes called smart materials, are materials which change their most basic properties, guys, based on, sorry, my phone is turned off. Which change their basic properties in response to external stimuli. That's pretty much probably a definition you'll find in Wikipedia, guys. You know, and it's correct. That's exactly what it is. So, for example, if you put that material somewhere in any microenvironment, biological or anywhere else, on cement, if there is the slightest crack or something changed, something moved, electric field fired through that material, the material, what will do? For example, if electric field change, electric field, what can do? Material will change its size, or will generate a magnetic moment, or something. There are many other things, right? So that's why there are many types of intelligent materials, and our favorite one is so-called magnetoelectric material. Magnetoelectric materials. There are 2 types of them. One is the first type, the most probably the basic. From the physics perspective type, it's called a multiferroic material. What it does is it combines at least 2 different fields in one phase. One phase in the crystal structure. So you have one crystal, and it responds to at least 2 different fields. You know what fields are. Magnetic, electric, electromagnetic, thermal, acoustic, anything. That's fields. Something, you know, you can control wirelessly, like that. And so to be called multiferroic, you need to be responsive to at least 2 different fields. The problem with those materials, most of them work only at extremely low temperatures, like superconductors. I'm sure you're familiar with superconductors at temperatures. Helium temperatures, 4K and below, you know. Otherwise, noise dominates the properties. Luckily, about a couple decades ago, they found out there is another way to create to create intelligence. In this case, magnetoelectricity. I'll tell you what it is. Using so-called core-shell structures or heterostructures, where you combine 2 different structures, and simple example, guys, is shown here. All right, if you look at that core shell drawing, you see that there is a core made of one crystal structure, and there is a shell made of a different crystal structure. But the materials are selected, designed so that the lattice matched right at the interface. At the surface interface, the lattice, at least in one dimension, perfectly matches. So what it means, if, for example, if one of the materials, in this case core, is magnetic, if I apply magnetic field, because of, most magnetic materials have the effect called magnetostriction. What means the magnetic field will change the distance, the adjacent distance between, the distance between adjacent atoms. So right at the interface, the distance between two adjacent atoms will change. But because that distance matches the distance in the shell at the interface, so what happens, you have, if you choose shell made of a piezo material, for example, with a right crystal structure, then what will happen, you will actually create piezo, you will activate piezo effect. And piezo effect, you know how, there are two types, direct and converse piezo effect. What means if you change the distance between adjacent atoms, you'll change an electric field. Electric dipole moment, guys, which will change the local electric field. So, these materials actually work very well at room temperature. There are quite a few of them, and they came up about 2 decades ago. And we were lucky to be the first ones who brought these materials into medical fields about a decade ago. It took us a long time to get to this point. It seems so simple, trivial, but you cannot imagine all the magic of chemical engineering and knowledge of quantum physics, actually, which we had to go through to come to this point, guys. So again, 24/7 for 10 years. So, guys, that's what we're doing. So now when we put these particles in the brain, guys, when neuron fires, you know what happens? There is a local electric field right next to the neuron. Wirelessly, you cannot detect that thing because the whole brain is electric. It's very complex electric circuitry. So there are major interference and charges in the brain screen off any electric field changes, local electric field changes. You cannot see anything outside. That's just not possible. So it cannot be done. So, but if you have these particles, what happens? The local electric fields changes into local magnetic field, which in turn can easily be detected. Easily, I exaggerate easily. Nothing is easy, by the way, let me tell you. Magnetic fields are relatively small, so you need quite special sensors there. Anyways, but that's it, that can be done. And so you can magnetically, if you have special, extremely sensitive magnetic sensors in your helmet, you can this way directly observe what's going on with your brain, what activity is taking place, quite precisely, by the way. And reciprocally, if you want to write information in the brain, for example, stimulate, that's what these guys want. They want the Air Force pilots to respond to emergency immediately. In that scale time, talking about 100 milliseconds, that's for them, it's immediate. What happens, you can send magnetic fields, which is much easier task, by the way, and right at the location of the particle. Guys, remember, magnetic field easily goes through the brain. That's why we have techniques such as magnetic resonance imaging, which is very popular, one of the most advanced imaging techniques in medicine, right? Unlike electric fields. Again, electric fields don't go through the brain wirelessly without interference. Magnetic go. So when magnetic field comes to the particle, because of the magnetoelectricity, that coupling between magnetic and electric field, because of that intelligence, changes that magnetic field energy into the energy of the electric field. So as a result, you generate local electric field because of that, and that electric field can be used to stimulate or to initiate an action potential, or they say to fire a neuron. So that's how our technology works, pretty much. Yeah, I described to you the basic physics of the technology we proposed, and this is what DARPA liked. DARPA thought it was one of the greatest, proposed there. Again, not modest to say. This is a little formula written, by the way, how we write information. Actually, I just described it to you, and how we read it back, right? It's a direct and a converse magnetoelectric effect we use. By the way, these expressions you see on the left, they're very linear. Not very linear, they are linear expressions. They're called Landau expressions of multiferroics. They're definitely not correct. That's I would say zeroth order approximation. We developed our own kind of physics here, which takes into account the nonlinear physics of those particles, quantum mechanics, etc. This, by the way, the materials we use are highly nonlinear. I think I'll show you one slide showing that, guys. There is hysteresis. Definitely, there's nothing linear there, guys. And if you don't do that, you cannot make it work. If you don't know that, if you don't take into account this stuff, you cannot nonlinearity. You cannot make these things work. This is our expertise. Something we've been doing for many years. By the way, on the right, you can see transmission electron microscopy image of such a core shell nanoparticle. It's about 20 nanometers in diameter. You clearly can see the core crystal structure. It's a high resolution TM image. And on the and shell, you can see also it has its own crystal structure. It's in one projection. It's not real three-dimensional crystallographic orientation, of course, because it's a TM projection, guys. If you're familiar how transmission electron microscopy works. But you clearly can see periodicity, and you can see the match in this particular at that particular interface, at the interface, the crystallographic match. That's it. That's the key to make sure you have a large magnetic-electricity. Fundamental limit of magnetic-electricity in the structures is very easy to estimate. All you have to do is to multiply magnetostrictive effect by the piezoelectric effect, right? And the maximum magnetic-electric coefficient you expect is on the order of 10 volts per centimeter per Ørsted. Ørsted is a unit of the magnetic field. We got something on that order, by the way. We measured, so we're definitely close to the maximum value. We published this recently, last year, time flies, during pandemic, this finding. This is the second paper. It's called a colossal magnetic-electric effect in core shell nanostructures. It's a major engineering work there. Again, I'm very grateful to my guys who managed to do that stuff. Guys, we're not limited to one material. We have millions of structures, combinations. We've been working for so long. So depending on the particular application, we can change, deviate. We do work actually, by the way, with totally different mechanisms to create magnetic electricity, which I think is much more advanced, by the way. I'm going to talk about this, not to bore you with this stuff, but it's a very exciting material science. It's called pyramid iron oxide nanoparticles. It's actually, this gives us lots of flexibility by building self-assembled pyramids, guys. As a result, what we do, we control not the dipole electric field. Well, the problem is dipole field, guys, the electric field is relatively small and it dies out very fast away from the dipole. In pyramid case, we can control the charge around the particle very much. So this is our, again, another invention. We're very proud of it, and we're definitely building up on this. And hopefully we'll be using it soon. And the good thing, by the way, we limited to one material. So remember, when we talk about human brain, there is another issue I never discussed here, is the biocompatibility. So all the materials I'm discussing are biocompatible, by the way. So that's all. That limits our engineering freedom here, guys, you understand. So if we need to use it for cement, for construction materials and so on, then of course there is no problem like this. But in medicine, there is a problem like this. So definitely that's why we do want to expand, guys. We believe, and I want a feedback from you. I already got some feedback from your department, guys, which we're very happy about, and I'll mention that. So guys, so now this is that nonlinearity I was talking about. As you can see MH loops of these particles. A very tricky way to measure it. We use scanning probe microscopy technique. We measure these properties at a single particle level. Again, guys, remember, every particle is on the order of 20 nanometers in diameter. It's very small. Measurements like this cannot be done by a regular device, right? So we pretty much had to build our device ourselves. Particularly my student who recently graduated, Ping Wang, did this stuff. And you can see quite well-defined hysteresis, guys. Definitely, it's not linear. There's nothing linear there, guys, right? Yes, I'm not going to get into detail, but that's what I was talking about when I said it's highly nonlinear. So if you don't take into account this nonlinearity, nothing will work. So this is, again, that's actually the slide from our collaborators. Battelle, they created the slide for us. They're very good in doing nice illustrations, these collaborators. So they showed, listen, guys, how we're going to do this when we're getting the DARPA project. They call it brain-computer interface or brain-machine interface, BCI or BMI. In this case, it's a wireless. It's a helmet. You put it on your head. You see, there is one drawing, one picture showing it. There are a bunch of sensors there. Easy to draw, by the way, but it took us a long time to actually put it in that scale. Again, major physics, lots of quantum physics to do that, guys. And so now particles. There are many ways to administrate it. The simplest is intravenous. One injection, guys. I had a picture here to show the injections. Now it looks like I don't have. Oh yeah, here. Look, you see on the left, it's a semi-transparent liquid. You inject micrograms of it or nanograms of it in your hand, and in your arm, and that's it. You become invincible, guys. And so that's what DARPA wants. DARPA wants to create a Superman, as I told you, right? So this is not necessarily we believe that's going to happen very soon, but anyways, that's what we're trying to do. And surprisingly, we're in the middle of phase 2, and you can imagine how far we went. Every month we had to demonstrate everything we promised, So we're pretty far, guys. Everything you see in drawings, we did it, So now we're very close to getting, we're actually doing rodent studies right now together with our collaborators in the Miami project, particularly Brian Noga. We're grateful to him. By the way, we rely on collaborators a lot here, guys, as you understand. Miami project, it's a short, for the Miami project to cure paralysis. It's one of the most funded projects in Miami, in South Florida, and actually in the world in this field. I'm sure you heard of it. It was founded by former football players, famous football players in the States, from Miami Dolphin, I believe. So the purpose is to cure paralysis. Is something still cannot be done. So they're very much interested in our ability to get inside the brain to control neurons. You understand the impact here, guys. If we learn how to do this very well, all the neurodegenerative diseases, the devastating diseases currently untreatable, Parkinson's, Alzheimer's, autism, the autism is a disorder, and many others, not just diseases, disorder, depression, major depression will be treated, guys. Will be treated because we can repair neural structure. All those diseases. By the way, I forgot to mention one of the most important brain diseases. People don't realize it's also brain disease. Glioblastomas, brain tumors, brain cancers is probably the most untreatable cancer, which develops extremely fast. Also will be treated. And we actually do things like this. So I'm just talking about this particular application. We do work with Sylvester Cancer Center on this, by the way. Our results are very promising. We did studies on animals and so on. And now we're going back to the DARPA stage. There are many phases. Now we're in the phase moving to monkey studies. Our monkey experiments will be done at Carnegie Mellon. Carnegie Mellon, there is an expert, our collaborator, Doug Weber, is a very famous scientist who does this monkey studies for robotics, etc. Uses new robotics devices for monkeys. And they're very excited about this opportunity. So they'll have to teach monkey using this technology to do certain operations. So that should take us a few months, by the way. We just started this, by the way. We send them devices, technologies, all these helmets and so on. Lots of stuff, by the way. I'm skipping a lot of information, you understand. If I actually show you all this stuff, probably my talk will take several days, you understand. So we started that part, guys. Now, you can see here, little movie here. It's how we got to this point. So first we do cell culture studies. We use hippocampus brain cell cultures. And you can see the little movie here, guys. Look, at some point, there is you see the whole thing lit up, guys. That's it. That's when we applied magnetic fields. And particles are there. There are so few of them, but it's enough to actually trigger an action potential in a neural network. And on the right, you can see scanning electron microscopy image of a neuron, guys. That's a soma here, with all the dendrites coming out and et cetera, et cetera. And it's tiny little particles here. Usually the particles concentrate at dendrites, which it can be understood why, because dendrites are much thinner. And remember, guys, the smaller the object, the more surface to volume ratio attached. So it makes sense. So there is more surface there, so particles tend to, with respect to the volume, particles to get this, agglomerated there. Not agglomerated, concentrated. And that's where we actually want to be. That's where signals in neurons start. And our purpose is to fire up the entire huge soma. Guys, you know, that's again, lots of challenges there. It took us a long time, a year to get to that point, guys. You cannot imagine the complexity of the brain. It's we start now. I have tremendous respect for nature. The engineering, guys, the nature, the physics there is mind-boggling, is underestimated. It's insanity. And I've been in this field for decades, and only now I actually realize, wow, how much more primitive we are than the nature is, by the way, in the knowledge nature gives us. So that's what we're trying to get to understand. It's all collective, guys. By the way, there is nothing binary. You know, the computing we use is binary, but definitely that's the most primitive computing you can do, right? You know, even our brain doesn't use binary for sure. You know, the logic is the following. If you ask me a question, my answers can be yes, no, or I don't know. It's already ternary, minimum, right? But you know, computer doesn't really do that. Computer is binary, simple. Modern computing, CMOS technology. Brain today, the more general consensus, I would say, is converging to the belief that the brain works in a 10 or maybe 12-dimensional space, guys. That's why it has such a parallelism on par with quantum computing. Most likely, ideas of quantum physics are already in the brain, guys. We just don't know how to see them. And now, by doing all this stuff, we see something of that sort. We're still far from understanding what exactly happens there, but we're starting to see certain trends, guys. So we are at the earliest stage. We're barely scratching the surface, but it's the beginning, right? The most important thing is to start. So guys, and here you can see the classic, traditional action potential. What you see is a calcium imaging of cells, neuronal cell cultures. You see, there are several examples, typical examples. You see on the left, there are 5 pulses. It says magnetic on top. And on the right, there are 5 or 3 pulses, it says electric. Electric signals are shown by red vertical lines, while magnetic signals are shown by blue lines. So you see that they're almost identical, guys. But please pay attention. Electric signals were triggered with wires. That's what Elon Musk technology did. Left signals were triggered by us magnetically. No wires used, guys. It's single neuron level. So what it means, this way we can approach every neuron in 80 billion neuron network, guys. Not just 1,000 neurons, guys. You understand? It's orders of magnitude better technology, guys. Yeah, I hope you understand the significance of this, guys. And I'm gonna skip this, not to bore you with this stuff. It's how you record information, guys. It's already 11:46. I noticed, you know. So this part is very technical. It's but I'll show you a little movie also on the rat. Our first, I would say, successful experiment in the mining project. Although we didn't have a chance to do many tests, guys. This is literally a few rats, and we were very excited to know only a few rats were enough to make things work, guys. What you can see right now, look, guys. We were not ready to this. It actually worked so fast, so we were not even recording immediately. So Manuel, our PhD graduate student who was building the setup, had his cell phone with him. And when we saw, okay, the whole thing is working, you see that the red, guys, it's moving its leg. There are no wires. We're actually making it move. We're in the other, we're doing it wirelessly, guys, using our technology, guys. So definitely, it's definitely working, guys. You understand? And this is what you see in the right pictures. It's all that setup we build. Here you can see Manuel, Shonos, our collaborator, and Mustafa in the picture. So guys, so you understand how excited we are about the whole thing, you know? Guys, I'll show the movie one more time if you skipped it, just in case. All right, so the movie again one more time. What that's we're taking a movie of our goal was to stimulate, to make the right leg of the rat move up and forward and back by sending signals. There are no wires, guys. Remember, no wires involved. That's a zoomed in picture. And the signals there, by the way, they are taken by EEG in parallel. EEG signals is electrodes attached to the other, to somewhere else in the body to record, to see if the signals we send, if the motion, local motion with induced wirelessly coincides with the actual electric signals in the brain. We measure using wires, and they do coincide for that particular experiment. So now where we're going with this, guys, you understand? You understand the significance. You know, I'm sure this presentation doesn't need conclusion section. It's obvious, right? How important and significant it is, guys. It's definitely. I'm not shy to say it's revolutionary. Now I want to bring this, guys, and it's very likely there are many other applications. So, guys, direct impact, guys. It's a two-sided impact here. First, we build the next generation information processing. We figure out how to make, we will really change the computing world, guys. We will be able to connect brain to artificial intelligence at such a level, guys. Again, this is something the DARPA guys said. It's a very arrogant sentence. It will bring Homo sapiens to the next level, guys. I know that's maybe too much to say, but that's exactly what was said. And the second application, the second input is probably more deep to me. That's how we started it, guys. Is to change the world of medicine. Medicine needs engineers today, guys, and we want to demonstrate to our medical partners, and who are very grateful to us, by the way. We thank them for working with us, that they cannot underestimate engineers. And this is an example. We can do incredible stuff for them. When we show it to these guys, their jaws drop. They could not imagine anything like this is possible. They could not even dream of anything like this, guys. You understand? So they